Hey there, and welcome. Look, if you've ever set foot in a chem lab, you know titration is like the fundamental skill. So today, we're going to break this whole thing down. We're talking a clear, step-by-step guide to nail it every time. Ready? Let's get into it. So how do chemists do that? It's a great question, right? Well, the answer is you have to become a chemical detective. And your number one tool? Titration. It's this awesome technique that lets us measure something we can't even see and turn it into a hard number. It's literally how we check if our drinking water is safe or figure out exactly how much copper is hiding in a chunk of rock. All right, here's the game plan for today. We'll start with the detective work, then get into the core principles, the why it all works. After that, we'll look at your toolkit, walk through the actual procedure, figure out how to crunch the numbers, and finish up with a quick quiz to lock it all in. Okay, first up, the chemistry detective. So what is titration really? How does this work? Okay, so here's the deal. Titration is basically a lab method where you use a solution you know the concentration of to figure out the concentration of one you don't. Let me put it this way. Imagine you've made some lemonade, but you have no idea how much lemon juice is in it. You could add a baking soda solution, which you know the strength of, drop by drop, until it's not sour anymore. Right? By measuring exactly how much baking soda it took, you can figure out exactly how much lemon juice you started with. That's it. That's titration in a nutshell. All right, so that's the what. Now for the why. Because, knowing the steps is great, but understanding why it works, that's the real key. So let's get into the core principles behind all this. So the experiments we're talking about really fall into two big buckets. Most of them, like the ones for alkalinity, iron, and copper, are what we call volumetric analysis. Super simple, we measure the volume of a solution to get our answer. But there's another kind, calorimetry, which we see in the heat of solution experiment. Here, instead of volume, we're measuring the change in heat or temperature. Kind of cool, right? Two different methods to hunt down the same unknown quantity. So, what's actually happening in the flask? It all comes down to a few key reactions. In the water alkalinity test, it's a simple neutralization. An acid and a base just cancel each other out. Easy enough. For iron and copper, it's a bit more of a dance. It's called a redox reaction. That just means one chemical is losing electrons, we call that oxidation, while another one is gaining them, that's reduction. They happen together always. And the magic moment we're looking for is when that electron swap is perfectly complete. Okay, time to gear up. Let's head over to the lab bench. Every good detective needs their toolkit, right? For us, that means reagents and, most importantly, indicators. So this is the big question. How do you know when to stop? How do you know when the reaction is perfectly done? That's where indicators come in. They're basically chemical referees. They watch the game, and the second the reaction is complete, they blow the whistle by changing color. It's our signal to stop. That color change is everything. And here it is, your official indicator cheat sheet. You're going to want to remember this. For the first part of the alkalinity test, we use phenolphthalein, and you're looking for a change from pink to colorless. For part 2, it's methyl orange, which goes from yellow to orange. For copper, we use starch, and that's a really dramatic deep blue that just vanishes to colorless. Now, the iron one is my favorite. Potassium permanganate, the stuff you're adding from the burette, is its own indicator. The solution stays colorless until the reaction is done, and then the very next drop turns the whole thing a faint pink. How cool is that? No extra referee needed. Sometimes in chemistry, you get these annoying side reactions that try to mess up your results. That's where something like the Zimmermann-Reinhardt reagent comes in. In the iron titration, this stuff is basically a bouncer. It stands at the door and makes sure no unwanted reactions get in and spoil the party. This keeps your endpoint super sharp and clear, so you get that sudden color change instead of a murky, confusing one. It's absolutely crucial for getting an accurate result. Okay, we know the why, we've got our toolkit, now let's get our hands dirty with the actual procedure. And the best part? Once you nail these steps, you can pretty much handle any titration that comes your way. It's a universal guide. But first, safety and accuracy. These are the non-negotiables, the golden rules. 1. Always rinse your burette with a little bit of the Titration first. Why? To get rid of any water that would mess up your concentration. 2. Read the burette from the bottom of the meniscus, that little curve the liquid makes. Be consistent. 3. Swirl that flask. You've got to keep swirling constantly so everything mixes properly. And 4, and this is maybe the most important, when you get close to the endpoint, slow down. Go drop by drop. Seriously, one drop can be the difference between success and failure. So here's the universal recipe for titration. Step 1, get your sample ready in the flask. Step 2, add just a couple drops of the right indicator. Step 3, write down your initial burette reading. Don't forget. Step 4, start adding the titrant, swirling as you go until you see that color change. Step 5, record your final reading. And Step 6, and you can't skip this, do it again. You need to repeat the whole thing at least a couple of times to make sure your results are solid. All right, you've done the hard work in the lab, you've been patient, you've been precise. Now for the payoff. Let's crunch the numbers and see what we found. Don't worry, the math isn't as scary as it looks. It's really just a checklist. First, find the average volume you used across your trials. Just subtract the initial reading from the final. Simple. Step 2, you need the known concentration of your standard solution. Step 3, grab the right conversion factor for what you're measuring. Then, Step 4, you just plug everything into the formula. And finally, Step 5, you calculate your final answer, whether it's a percentage or parts per million. Let's take the iron calculation as an example. See this formula? The amount of iron is just the volume of the potassium permanganate you added, times its normality, times a special number just for iron. That's it. It's totally plug and play once you've got your numbers from the lab. Okay, we have covered a ton of ground. We've talked about the what, the why, and the how. So to make sure it all sinks in, let's do a quick recap and a little quiz. Quiz time. First up, in the alkalinity test, you use phenolphthalein for the first endpoint, but which indicator do you need to find the total alkalinity? Think about it. The answer is methyl orange. Remember, phenolphthalein only gets you part of the way there. Methyl orange is what you need to measure everything, and it gives you that signature yellow to orange signal. All right, question number 2. This one's a little trickier. In the copper estimation lab, there's that weird step where you have to put the flask in the dark for 5 minutes. What's that all about? Why do we do that? And the answer is because that reaction needs time to finish. It's not instant. That 5 minutes in the dark is to make sure every last bit of the copper has reacted with the potassium iodide. That reaction releases iodine, and it's the iodine we're actually titrating. So if you skip that step, your result will be totally wrong. It is absolutely crucial. And hey, let's not forget our other experiment type, the heat of solution. That's just the energy change you can measure when you dissolve something. It either gets hotter or colder. All we do is measure that temperature change. It's a great reminder that our detective work isn't always about volume. Sometimes it's all about the heat. So there you have it. You can see just how powerful titration is. And look, this isn't just some random lab exercise you have to get through. This is real-world chemical detective work. It's used every single day, in medicine, in food, in protecting our environment. It's one of the hidden sciences that keeps our world safe and running. So the only question left is, what are you going to discover with it?